Hello everyone, and welcome to this video on section 5.1 called Sequences. In this video, I'm going to be taking you through a preview version of a Newton Alta assignment for section 5.1 Sequences. Please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself, but the objective should be the same. And hopefully the problems are similar enough that watching me do these here will help you out when you work on it on your own. All right. So here's your assignment page. You won't have the word preview, but you get a title of the section in the upper left-hand corner. Upper right-hand corner, you got your mastery bar, which tells you how far along you've gotten in the assignment. Next to that, you have your activity log, which shows you all the objectives of the assignment and your progress in them. And that looks like there are 7 objectives here, so this may be a long video, I'm sorry. Then you have your current objective and a question beneath related to that objective. And at the bottom of every question, you should be seeing a feedback button where you can send feedback directly to Newton. Use this if you're seeing any typographical errors or problems with the answer, explanations, or something like that. And hopefully they can fix things. The instructor cheat button will not be there for you, right? This is for instructors only. But you should also see the more instruction button. So if you're ever struggling with a topic or a question, click on this and it'll take you to another page with some reading to do or videos to watch or both. And then you'll be given a question related to that instruction. And you can work through the entire assignment that way if you wish. You can click on more instruction, every single time a new question comes up and work through it that way. Nothing wrong with that. Okay, so here we are starting with this objective. Find the formula for the nth term of a sequence. All right, so what we're given terms of a sequence of numbers. Here I'm given the first, it looks like 6 terms of this sequence. And we're asked to, see the little dot, dot, dot here. You're asked to then go about and figure a formula that will give you the general term, what the general term of this sequence looks like. So they're saying, identify the explicit formula for the nth term of the sequence written below. Note that the first term is for n equals 1. Right? So they're telling us that, when n equals 1, I need to have an output of -5. And that's really what a sequence is. It's an input-output function where my inputs will be integers, whole numbers. So input 1 gives me output 5. Input 2 gives me output 25 halves. Input 3 gives me output, -125/3, and so on. And yeah, they're just asking for a general rule for this function. When I input in, what do I get as an output? Now this is a multiple choice question. All right, but so you could go through every single one of these rules individually and just see which one matches the sequence they gave you. Take the first rule here, replace n with 1, see if you get -5. And you wouldn't get -5 there, so it's not the first one. The second rule, if I replace n with 1, I would get -5. If I replace n with 2, I would get positive 25 halves. If I replace n with 3, I would get -125 thirds. Yeah, so just based on the first several terms, I think it's going to be this one. Because, yeah, look at these last ones here. Yeah, the third one, when you plug in 1 for n, you'd get, -5 halves for the first term. But it's -5, so that's not it. Then the last rule here, you plug in 1 for n, yeah, you get -5 halves. But if you plug in 2 for n, you'd get -25, -5. When you plug in 1 for n, you get -5. Great, but when you plug in 2 for n, you get -25 halves, not positive 25 halves, right? Because you got this -1 here all the time in the front. So it's going to be the second rule, but I want to go through and talk about what we're looking at here on paper. And so here was this sequence. Right? The first term was -5. Then the second term, positive 25 halves. Third term, -125 thirds. Fourth term, 625, fourths. And I'll stop there. I know they give me 2 more. But this should be enough to figure out what's going on here. In fact, I'm going to write this first term as, -5/1. All right, so they tell me they start off with n equals 1. So this is like typical sequence notation. So suppose I call this sequence A, and the subscript A sub 1 here just tells me I'm looking at the first term, right? And A sub n is the nth term of the sequence, right? So the subscript tells me what term I'm at. And like I said earlier, this is just a function. I'm going to input n and get some output that'll be one of these terms of the sequence. So we have -5, right? -5/1 for A sub 1. Then positive 25 halves for the second term. Now, I'm noticing an alternating here. All right, so again, I'm just going to point out things that you might see in other sequences in the future. I'm noticing this alternating here, positive then negative, positive then negative, This is what they would call an alternating sequence. The sign is changing from negative to positive, positive to negative, negative to positive, right? When you see an alternating sequence, you're going to have -1 at some power as part of the term, the general formula, the explicit formula for the terms of the sequence. So like in my first term here, this is -1 to the first power times, 5/1. That's -5. Second term, we have -1 to the second power. Remember, -1 to an even power gives me positive 1. And then, first term, you had 5 to the first. 25 is, 5 squared over 2. I'm trying to just kind of get a general little rule here. Hopefully we can see a pattern after writing out several terms. So A3, the third term, is negative, 125 over 3. And think of this -1 here as, -1 to the third. That's, it's using the index. -1 to the third power would be -1. And then 125 is, 5 times 5 times 5. That's 5 to the third, and then you got a denominator of 3. And so on. Okay, so like this last one, 625 fourths, that's -1 to the fourth, which would be +1. Numerator is 5 to the fourth power. Denominator is 4. So it's looking like here, and again, I already toggled the answer, but it looks like every single one of these terms, A sub n is -1 to that nth power times, and then that power of 5, A2 had 5 squared, A1 had 5 to the first, A3 had 5 cubed in the numerator, right? So times that power of 5 over, and then the denominator was just whatever the term number was. Now that term number is also referred to as the index. So here I have an index of 3, but that's also my denominator, 2, 2, 1, 1, n, n. So this looks like a good rule for our sequence terms, a good function. And again, check it out. Replace n with 1, you get -5. Replace n with 2, you get 25 halves. Replace n with 3, you get -125 thirds, and so on. And this would also be called, they were calling this an explicit formula for the terms of the sequence, right? An explicit formula means if you want to know the 100th term, you can just plug in 100. Right? You know the actual rule for each term. You can just plug in that number and get what the term is. If I wanted 100th term, that'd be -1 to the 100th times 5 to the 100th over 100. A crazy big number there, but that's what an explicit formula is. It's you know the rule for every single term, and to find the nth term of the sequence, you just need to plug in the value of n. All right, so back on the assignment. All right, like I said, it's multiple choice, so I already just kind of ran through these 4 earlier out loud. This second rule satisfies, the sequence matches up with the terms of those sequence. So I'll submit. Wonderful. And after every single question, right, whether you get it right or wrong, there is an answer explanation. Please read through these. If you're wrong, make sure you can understand. Hopefully you can figure out where you went wrong while reading through the answer explanations. And even if you were correct, maybe on this you guessed. Don't guess though. Remember Newton Alta. It's adaptive, so if you start guessing things wrong, right, it's going to make the assignment longer and longer until you master things. But say you guessed this and didn't understand why you were right, try to figure out why you were right down here. Or maybe you knew how to do it, but they do it some other way that you like better, and you might want to use for future problems. Okay, so let's continue. All right, so now we're just asked to write the terms of a sequence, given some description of that sequence. All right, so we saw in the first example an explicit formula where I knew what the function was. I could tell you what the 100th term was by just plugging in 100, or the 1000th term by just plugging in 1000. This here, we're given what's called a recursively defined sequence. It says write the first 4 terms of the sequence defined recursively by the equation below. So this is what they call a recursive formula. In a recursive formula, you're given some terms of the sequence. So here I'm given the 0th term, right? Last example, they started at 1. Here, they're starting at 0. Again, you're going to start at some integer and then work your way up. Just keep increasing the term number by one at a time. So here we're starting at a sub 0. So the initial term of the sequence is -2. And then what makes this recursive is that they define after that, they tell you how every term is related to previous terms. So you see this a sub n plus 1 equals -6 times a sub n plus 2/3. So this means that every term after that, all right, the n plus first term is, the previous term, right? You see how the subscript is 1 less n plus 1 to n? So it's the previous term, a sub n, multiplied by -6, and then you take that product and add 2/3, right? And it says you may enter an exact answer or round to 2 decimal places. Okay. So we put this on some paper here. We'll talk about it. Write out the first several terms of this. So yeah, so they tell us, right, a sub 0, the initial term of this sequence, is -2. And then after that, right, a sub n plus 1 is negative 6 times a sub n. So again, every term is negative 6 times the previous term, right, n plus 1 to n, one term before, then plus 2/3. All right, so again, we know a sub 0. So we can use this here. If I plug in 0 for n, we can find a sub 1, right? So I'm going to plug in 0 for n first. That gives me on the left side here a sub, 0 plus 1. So a sub 1, the next term in the sequence, will be negative 6 times a sub, and again, I'm replacing n with 0 throughout this rule, a sub 0 plus 2/3. Now, a sub 0, right, the 0th term or the initial term of the sequence we know is negative 2. So this is negative 6 times negative 2 plus 2/3. Well, that's positive 12 plus 2/3. Now, they did say we could round to 2 decimal places or, write an exact answer. This would be, this is 12 over 1. Multiplied by 3 over 3, this would be 36 over 3. All right, 36/3 plus 2/3 would be 38/3. Okay, so when I start writing out the sequence up here, we got negative 2 for the initial term. The next term is, 38/3, which is 12 and 2/3, or 12.66666. If I rounded to 2 decimal places, that'd be about 12.67. All right, so now I got the A1, and they want the next 4 terms. They want A1, A2, A3, and A4. Okay, so I got A1, and now I'll just keep increasing the value of n by 1. All right, we have A1 now. I need to find A2. So in order to get A2 over here, I need n to be 1, right? So just increase the value of n by 1, increase the input by 1. And on the left side of this rule, we'll have A sub 2 equals, negative 6 times, A sub 1. Then after that, plus 2/3. And we know what A sub 1 is, right? So this would be negative 6. A sub 1 we saw in the previous line when it was 38/3. And then plus 2/3. Right now I'm going to do some simplification here. 3 goes into 6 twice. This would be negative 2 times 38. You know what? I should have just kept that as 3 because I need to add to this fraction. So forget that then. So I'm just going to keep the 3 in the denominator here. So that way I can put the fractions together, right? Get a common denominator when you add or subtract. So this is still negative 6. Now 6 times 38, 6 times 30 is 180. 6 times 8 is 48. 180 plus 48 is 228. So this is negative 228 plus 2. All right, so negative 226 thirds, right? There, that's the next term, negative 226 thirds, which again, you can round that to 2 decimal places if you want. Yeah, that'd be negative 228 plus 2, negative 226 thirds, right? Great. So now I've got A2. And let's keep going. So now I increase the value of n by 1 to get the next term. When n is 2, you'd have a sub 3, the third term, or the fourth term, because, we start with a sub 0, but the a sub 3, you can just follow the rule. Replacing n with 2 would be negative 6 times a sub 2 plus 2/3. And we know a sub 2 from the previous line, right? This would be negative 6 times, and then negative 226 thirds. And then we're adding, 2/3 to this. Oops, sorry. Now, a negative times a negative will be positive. And that's 1,200 plus 120, so 1320 plus 36. This is positive 1356 plus 2. So 1358, 1,358 thirds. Great. So that's A3, 1,358 thirds. And then I need A4 as well. So I'm going to just, again, increase the value of n by 1. So n equals 3. And once again, go through this rule here, replacing n with 3. Give me a sub 4 on the left is negative 6 times a sub 3, and then plus 2/3. And we know what a sub 3 is from the previous line, right? This is negative 6. The third a sub 3 here was, 1,358 over 3. And then we're adding 2/3. Again, I'm just going to multiply up here. So that's 6,000, right? And 6 times 300 would be 1,800. 6 times 50 would be 300, and then 6 times 8 is 48. So this is 60, 78, 8148. All right. And then plus, so we have negative, right? And we're adding all these together. So this is negative 8,148 thirds plus 2/3. So negative 8,146 thirds. And there's your term of the sequence. Negative 8,146 thirds. Next term. Okay. And that's all they want. I'm just going to enter them in their exact forms. Again, you could have used a calculator and decided to round these to 2 decimal places, but I'll enter them as their fractions. So we saw A1, right, was 38 thirds. Then A2, negative 226 thirds. A3, 1,358 thirds. And A4, negative 8,146 thirds. Right? So hopefully I didn't make any arithmetic mistakes. Wonderful. All right. Yeah, so they have the fractions there. Again, they said you could have entered decimal, so if you want to use a calculator, fine. I could have pulled up Desmos here and started calculating those things, but I'll pull up Desmos at a later point. These are just some fractions, and they take you through the answers, of course. All right, moving on. All right, so once again, we're given a recursive formula. It says, you see, the sequence is defined recursively. So we have a sub 0, right? The initial term, they're starting at 0 again, is 3. And a sub n is 2 times, a sub n minus 1. So the nth term of the sequence is 2 times the n minus first term, which is just 1 before it. So every term is 2 times the previous term. Now, this is what they were referred to as a geometric sequence, right? Every term is just the same number, multiple of the previous term, right? You multiply with the same number every time to get from one term to the next. Now, we don't need to know that it's called a geometric sequence to work with it, okay? And this time they want us to take this recursive formula and write an explicit, right? I want you to determine the explicit formula. So you see down here it says a sub n equals. So what they want here is a function of n. Give me some expression that depends only on n, not a sub n minus 1, right? That an expression that depends only on n, that'll tell you what the nth term of this sequence is. And, something where you don't need to know what previous terms are to figure it out. So again, we're given a sub 0 is, 3. And this is our recursive rule that, every term is just 2 times the previous term. Right? So that means a sub 1 would be 3 times a sub 0. So 2 times. I said 2 times, didn't I? A sub 1 is 2 times 3. And then a sub 2, so I know that would be 6, fine, but I'm going to leave it this way for now. And then a sub 2 would be 2 times, the previous term, which if you do 2 times 2, that's 2 squared times 3, right? And so that would just be the previous term times 2, that's 12. And then the third term, that would be 2 times the previous term, 2 times 2 squared times 3, which will be 2 to the third times 3. Now I know that'll be 24. But hopefully you can see what's happening here. Now every term is just 2 to that power, right, times 3. See, a2 is 2 squared times 3. a3 is 2 cubed times 3. So it looks to me like a sub n here is 2 to the nth times 3. And you can test it out. When n is 0, you have 2 to the 0 times 3. That's 1 times 3, that's 3. And when n is 1, you get 6. When n is 2, you'd get 12. When n is 3, you'd get 24. So here's an explicit formula. 2 to the nth times 3, or, 3 times 2 to the nth. So down here, I'll put it that way, 3 times, and then 2, raised to the nth power is an explicit formula for our sequence. Great. And moving on. All right, so once again, we're just asked to write out, and enter exact answers. Write out the first 4 terms. They say starting with n equals 1 this time, not 0. So what's a1, a2, a3, a4 for, this sequence. And here they give us an explicitly defined sequence, right? Every term is just, the index minus 1 divided by 4 squared, right? To figure out what the 5th term is, I just plug in 5 for n. To figure out what the 100th term is, I would just plug in 100 for n, right? This is explicitly defined. So I don't need to know what previous terms are to get the next one, right? Okay, so yeah, I will write this in. Now, they do say enter an exact answer. Now, I mentioned earlier, you can use a calculator for these, right? When you have an explicit formula, these are functions. These are just like functions. I've got a sub n equals n minus 1 divided by 4, to the second power here. This is a function of n. All right, so I could go to calculator like the Desmos site, desmos.com, and put in like f of n. It's a function of n. F of n equals n minus 1 divided by 4. I don't know, let's square all this. So parentheses around all that. And then squared. And now I know you're seeing a graph for like all real values of n. We're only plugging in whole numbers, starting with n equals 1. So I can make a table here, go to settings, make a table. And then the left side is, they're calling it x1, but it's the value of n, right? My input. So when n equals 1, I get 0. When n equals 2, now unfortunately, you got decimals here. and you don't see how to change them to fractions. But I could do this instead. I had f of n equals this and go what's f of 1? That's 0. What's f of 2? And then you can change individual values like this. You can't change the values in tables, but you can, off to the left here, you see my cursor. It's off to the left. You can't see it, but there's this little fraction button to be 1/16. All right. And then just keep going. What's f of 3? The third term. That's a quarter when I change it to a fraction. And then f of 4, and that's all they want, right? I could keep scrolling down like this, change this to a fraction, 9/16, right? So we get first term would be 0, second term would be 1/16, third term would be 1/4, fourth term would be 9/16. All right. Now, you are seeing that, you can easily do this by hand as well. We saw this earlier in an earlier example. A sub 1, replace n with 1 would be, 1 minus 1 over 4 squared, but that's just 0. Right, 0 divided by 4 is 0, and squared is 0. Then a sub 2, right, just replace n with 2, input 2. 2 minus 1, divided by 4 squared, that's, 1 over 4 squared, that's 1/16, like I showed you in the calculator. A sub 3, right, again, just replace n with 3 in the rule. 3 minus 1 divided by 4 squared. Well, this is 2 over 4, that's a half squared, so that'd be a quarter. Right, and then a sub 4, and this is as far as they want you to go, is 4 minus 1 divided by 4 squared. Well, that'd be 3/4 squared, 9/16, right? So I get the same results by hand as I do in the calculator, of course, and I'll enter those in the assignment. So let me actually skip all these for later. All right. So yeah, so 0 for A1, 1/16 for A2, A3 was 1/4, and A4 was 9/16. Great. All right. Okay, so this time there's no multiple choice, right? We're asked to find the formula, an explicit formula, right? So get a function of n and n only. I want this thing to depend on n, so that when I plug in a value of n, starting with n equals 1, I get these outputs. So when n equals 1, I want the output to be 6. When n equals 2, I want the output to be -18. When n equals 3, I want the output to be, positive 72, and so on. Right, so let's write this out. So like I said, we want a sub 1 to be 6. We want a sub 2 to be -18. A sub 3 to be positive 72. A sub 4 to be negative 324, and so on. Uh, you if I were to factor these things, right, so I'm seeing an alternating first, right? I see an alternation, right? It's positive, then negative, then positive, then negative. So I know the rule is going to have -1 to some power, but I want to make sure it starts off positive when n equals 1, right? If I had just -1 to the nth, -1 to the first power is negative. So I'll do this. I'll throw on -1 to the n plus 1. Or you could do n minus 1. But that'll make sure I have the positive, negative, positive, negative. Right? When n equals 1, this would be -1 squared, so positive 1. When n equals 2, this would be -1 to the third, so -1, and so on. Right? This will give me an alternating that I want. All right. So I'll put that in the rule, just because I see that it's alternating positive, negative, positive, negative. And you know what? I'll put in A5 as well, and A6. So we had positive, 7,776 over 5, and A sub 6, right? The sixth term was negative 7,776 All right. Okay. Now this fifth term is giving me a clue. See how the index is 5 and you got this denominator of 5. So I'm thinking I'm going to try to rewrite these so that the denominator is the same as the index and see what happens. So this is 6 over 1. This would be negative, 36 over 2 multiplied by 2 over 2. And if I want this third term to have a denominator of 3, 3 times 72 would be 216 over 3. And then this multiplied by 4 over 4 would be negative, 324 times 4 would be 1296. And then over 4, and then you got, 7,776 over 5. All these numerators. 6, 36 is 6 squared. Times 6 again would be 216, that's 6 cubed. 1296 is this times 6 again. All right, it'd be 1290. Yeah, this is 6 to the 4th, and this is 6 to the 5th. All right, so now I see it. All right, so yeah, I needed to go out to that 5th term to really get the pattern down. It's some power of -1, so it's alternating, -1 to the n plus first power here. So that it alternates positive, negative, positive, negative. And then every term, every term has a power of 6, 6 to the first, 6 to the second, 6 to the third, 6 to the fourth in the numerator, so times 6 to the nth. But then over, the denominator is the same as the index. So here we go. This is what I'm going to type in. All right. So yeah, this is not really something that can be taught very well, I don't think. It's just about your ability to be able to see patterns, right? For the most part, right, if I'm trying to find a general formula for a sub n, I try to think of how do I work the n into the expression on the other side? How do I work the index? And that's why this fifth term gave me a clue. That, ooh, maybe maybe if I rewrote everything so that the denominator was the same as the index, I'll see something. If that weren't there, I might have had some trouble trying to figure out what the pattern was. So yeah, that's definitely the hardest part about these is, seeing the pattern. And nothing that can really be taught. It's just through experience, more and more practice with these. Hopefully you'll get better and better at recognizing these patterns. So I'm going to type this for my rule, my explicit formula. So we have a sub n here is, -1 raised to the n plus 1 power, or n minus 1. However you want to make it alternate positive, negative, times 6 to the nth, right? So times and then 6 to the nth power divided by n. Great. All right, so they use parentheses. I use the times symbol, whatever. But yeah, so they have exactly the same rule. Wonderful. All right, moving on. All right, so there's another one where I'm starting with n equals 1. So when I plug in 1 for n, I want to get 1/4. When I plug in 2 for n, I want to get 1/3. 3 for n, I want to get 2/5, and so on. All right. Yeah, so let me write some of these out. And again, hopefully we can see some sort of pattern forming so I can write an explicit formula for the general nth term. Okay, so they want us to start with n equals 1. All right, so a sub 1, they said was, 1/4. A sub 2, right, the second term. 1/3. A sub 3. 2/5. a sub 4, 4 ninths, a sub 5, 8 17ths, and a sub 6, 16 over 33. All right. Now, I guess a tip I would give to you is first check to see if it's in a nice kind of sequence. I would ask myself, is it arithmetic? Sorry, misspelled that. Arithmetic or geometric? Now, arithmetic means you add the same thing every time. So I'd add the same number to get from one term to the next. Geometric means you multiply by the same number every time. Now, to test for arithmetic, you just take differences between consecutive terms. Take the a2 minus a1. That'd be 1/3, minus 1/4. Well, that's 4/12 minus 3/12. So that's 1/12. And then a3, and take a3 minus a2. 2/5 minus 1/3. This is not 1/12. Okay, so not arithmetic. Remember, an arithmetic sequence, you have the same number being added, so you have this common difference between consecutive terms. The difference between consecutive terms would always be the same. So not arithmetic. And, geometric means you're multiplying by the same thing every time. So that means the ratio of consecutive terms will always be the same. So I take a2 divided by a1. Well, that would be 1/3, divided by 1/4. That's 1/3, times 4. That'd be 4/3. And then take the next two terms, a3 divided by a2. 2/5 divided by 1/3. This would be 6/5, right? So these are not the same. So it's not geometric either, right? So that, again, I could see that already. I'm just telling you, this should be a good thing to test first. Just eyeball it, or actually write things out. Do I add the same thing every time? No. Do I multiply by the same thing every time? No. But if you did, right, if it was arithmetic or it was geometric, that would make it a lot easier to find the rule. All right, well, it is neither of those things. So now I got to think of something else. Well, what I'm noticing in these last, actually from A2 onward, doesn't really work so much for A1. But like A6 down here, all right. I'm noticing all the, again, at least from A2 onward, powers in the numerator, the numerators are powers of 2. So this is like, 2 to the 4th power here is 16. And then the denominator is 1 more than the next power of 2. 2 to the 5th would be 32, and then you're adding 1 to get 33. Same thing here. The numerator is 2 to the 3rd, and then this is 16 plus 1, 2 to the 4th plus 1. And then for A4, the numerator is 2 squared. And then, this is 2 cubed plus 1 in the denominator. And then here, A3, this is 2 to the 1st in the numerator, and then 2 squared plus 1 in the denominator. And then here we have 2 to the 0 in the numerator, at 1, and then 2 to the 1st plus 1 in the denominator. The only issue, oh, this actually might work out. Let's see. A1, let's see if I keep backing this up. 2 to the negative 1st power divided by, and then 2 to the 0 plus 1, this does work. This is a half, right? 2 to the negative first, and then divided by 1 plus 1 divided by 2. That is a quarter. Wonderful. Ooh, okay. So I was worried there, but this pattern does seem to follow every single time. So it looks like a sub n here. Now notice for a6, the power in the numerator was 2 less, right? Same thing for a5, a4. So we have a 2 to the n minus 2 power in the numerator. And then you got one higher power of 2 and then plus 1 the denominator. So 2 to the n minus 1, when I add 1 to n minus 2, I'd get n minus 1. And then you're adding 1 to that. Right? So it looks like this is the rule for the terms of this sequence. Yeah, so that was a bit of a tricky one, but it started off with me noticing that there are powers of 2 in the numerators. Right? That's really where it started for me when I was trying to recognize the pattern here. All right, so we have in the numerators, 2 raised to the n minus 2 power divided by, and then 2 raised to the 1 less than that. Sorry, 1 more than that, 2 to the n minus 1 power, and then after that plus 1 all in the denominator. And I think that should work out. All right, so ours is not exactly the same looking as theirs, but still works. All right, yeah, so they multiplied the top and bottom by 4. All right, it's still the same expression though. They just multiplied the numerator and denominator of our thing by 4 for some reason. All right, great. So moving on. Again, really tough. I know it can be difficult to see the pattern. All right, now this time I'm just going to go through the multiple choice. This is nice. This is like the first example from the video, right, where it's multiple choice. So look through the choices and see which ones give you what you want. So I'm asked to write a pattern for write a rule, an explicit formula for this sequence. Again, starting with n equals 1. So I would like when I plug in 1 to get 1/3. When I plug in 2 for n to get 2/5, and 3 give me 4/9, and so on. Actually, these are all the same terms that I was getting in the last problem. So this is 2 to the 0 over 2 to the 1 plus 1. And then this is 2 to the first over 2 to the second plus 1. So it looks like it's 2 to the n minus 1 over 2 to the nth plus 1. And then if I multiply the top and bottom by 2, I'm getting this rule here. Right? So it's got to be the second rule. And let's check it out, right? When I plug in 1, so you have 2 to the nth in the numerator divided by, and then 2 to the n plus 1 power plus 2 in the denominator. When I plug in 1 for n, you'd have 2 over, 6, which is 1/3. When I plug in 2 for n, it would be 4/10, which is 2/5. When I plug in 3 for n, you'd have 8/18, right, which would be 4/9. Okay, so this second rule here is matching the terms from this sequence. Great. All right, so 1 of 7 objective is now complete. All right, so we're back to just writing out the terms of a sequence. All right, now this one, they give us a recursive rule again, right? So remember, recursive rules tell me if I need to get a term in the sequence, I need to go back to other terms. I need to know previous terms. I can't just plug in the value of n and get it. So here we have a sub n plus 1 is equal to negative 1/2 times a sub n. All right, so this is saying that every term is, the previous term times negative 1/2. All right, so I'm just going to say these ones out loud, actually, right? So notice the 0th term, the initial term is negative 1. So according to our rule here, the next term, a1, would be negative 1 times negative 1/2. So positive 1/2 for a1. And then I take that term and multiply by negative 1/2, right? The rule is just take every term and multiply the previous term, multiply the previous term by negative 1/2. So for a2, that's going to be A1 times negative half. So a half times negative half, that would be negative 1/4. And then A3 would be negative 1/4 times negative 1/2, which would be positive 1/8. And then A4 would be 1/8 times negative 1/2 would be negative 1/16. And that's it. They only want those terms. Great. So again, recursive rules tell you how to take previous terms to get new ones. Explicit rules, you just have to plug in the value of n. You don't need to know previous terms. Explicit rules. Great. All right. So this one I'll actually write out. All right, this is a little more complicated than the last one. Right, the last one was just keep multiplying by negative half. So here we have the initial term of the sequence is negative 1. And then every term is negative half times the reciprocal of the previous term. You see how it's a sub n to the minus 1 power, and then minus 3, right? So it's a little more complicated. So I will actually write this one out. So again, we have the initial term a sub 0, negative 1, and then the rule for the rest of the terms, right? Every term a sub n plus 1 is negative half times, and then they have a sub n, but to the minus 1 power. This is the reciprocal of a sub n and then minus 3. So you could think of this as negative 1/2 times, and then 1 over a sub n, right? The reciprocal of the previous term, minus 3. Okay. So a sub 1, according to this rule, is going to be negative half times, and then the reciprocal of negative 1, 1 over negative 1 is negative 1 again, all right? And then minus 3, well, that's positive 1/2, minus 3, that's 1/2 minus 6 halves, that's negative 5 halves. All right, so there's the A1. All right, then A2, and follow the rule, will be negative 1/2 times the reciprocal of the previous term. Previous term was negative 5 halves, so this is going to be negative 2/5. And then minus 3. Now 2's cancel, and you have positive 1/5 minus 3. So that's 1/5 minus, this would be 15/5. 1/5 minus 15/5 would be negative 14/5. All right, so negative 5 halves, negative 14/5. Now on to A3. The next term of the sequence will be according to the rule, negative 1/2 times, and the reciprocal of the previous term. The previous term was negative 14/5. All right, so flip that over. That'd be negative 5/14, and then minus 3. All right, now this nothing cancels. This is positive 5/28, minus 3. Again, this is 3 over 1. And if I multiply by 28 over 28, get a common denominator here. 3 times 28 is 60, and 24 is 84. 5 minus 84 would be negative 79/28. Right? So there's the A3. Right? Again, technically that's the fourth term of this sequence because it started with 0. But there's the next term, negative 79/28. And I'm pretty sure that doesn't. Yeah, it doesn't. That's not even or a multiple of 7. All right. And then finally, they want, up to A4, follow the rule, right? This is negative half times, and the reciprocal of the previous term. So that'd be negative, 28/79, and then minus 3. Now here I can do some simplifying, right? 2 goes into 28 14 times. So this would be positive 14/79 minus, and then 3 over 1. Multiply this by 79 over 79, get a common denominator. Now 3 times 79, that's 210 plus 27. So that's 237. All right. Now 237 minus 14 would be 223. So this is the opposite of that. This is negative 223 79ths, right? So there's your final term that they're asking for. All right, so I'll type those in. A1 we saw was, negative 5 halves. They also said you could enter these into calculators and round to 2 decimal places, but I'm just going to keep entering the exact answers. Negative 14 fifths was the the third term, A2. And then negative 79 28 for the A3. And A4 was negative 223 79ths. Right. Hopefully I didn't make any arithmetic errors. Great. All right, moving on. All right, so this time, right, they give me an explicit formula. So to get the nth term, I just plug an n, right, to get the output, to get the sequence term. I don't need to know what previous terms were, like in a recursive formula. Okay, so when n equals 1, negative 8 to the first would be negative 8. And then times, negative 1 would be positive 8 over 3. So A1 is positive 8/3. And then all I'm really doing is multiplying each of these things by negative 8. Right? When I increase the power by 1 here, you're just adding another factor of negative 8. So when n equals 2, you'd get negative, 64/3. And then times negative 8 again. Now 8 times 64, that'd be 512, right? 480 and 32, so positive 512 over 3. And then times negative 8 again, so negative, now 8 times 512, would be 4,096. So negative 4,096 over 3. And those will be the first 4 terms of the sequence defined by this rule. Great. All right, let's go on. All right, so one more time here, a nice easy rule where they give it to us, an explicit rule. So all I need to do, right, is plug in values of n and enter, the first 4 terms here, starting with 1. Now 8 is 24/3. So this is like 13n minus 24 all over 3. Now when n equals 1, you got 13 minus 24. That'd be a negative 11/3 for A1. Just plug in 1. And then I would just keep adding 13 to the numerator. Because again, it would be 13n minus 24 all over 3. And every time I increase n by 1, it would increase the numerator by 13. So negative 11/3, and then increase the numerator by 13. Negative 11 plus 13 would be positive 2/3, right? Positive 2/3. And then increase the numerator by 13. That would be positive 15/3, which is 5. All right, 15/3. And then increase, 15/3, increase the numerator by 13, that'd be 28/3. All right, so when n equals 1, you get this, n equals 2, you get this, n equals 3, n equals 4. And there you go. Great. So explicit formulas should be pretty simple, right? You're just plugging in values of n, getting them. The recursive formulas, I feel like people have a harder time with. Remember, you just got to get one term, you need to know some previous terms in those recursive formulas. Okay, so we're done with that objective. Moving on. All right, so now we're into determine the limit of a sequence graphically. All right, so limit of a sequence, we're looking at these sequences and we're going to see what happens to the sequence values as you go to infinity, right? As you just keep going further and further along the sequence. And what happens to those terms? Are they approaching some finite value or not? And if they approach some finite value, they call that a convergent sequence. If they don't approach some finite value, call that a divergent sequence, right? And it's got to be a single finite value, not multiples. Yeah, so here we got determine the limit of the sequence whose first 10 terms are shown below. Let me click on a point, see what the terms are, right? So like the first term of this sequence is negative 3.374. The second term is 0.14. The third term is negative 0.052. The fourth term is 0.02. The fifth term is negative 0.007. The sixth term is 0.003. The seventh term is negative 0.001. The eighth term is 0. Ninth term, 0. 10th term, 0. So you see how the terms of this sequence, see how these points here are approaching the horizontal axis where the output is 0? Looks like, all the terms, all the outputs here are approaching 0. So as we get further and further to the right, as you continue on to, look at terms further and further down along the line in this sequence, the terms are approaching 0. So it's and it's just like limits in calculus, really it is. The limit as n approaches infinity of the terms of this sequence looks like 0, just based on the first 10 terms of this graph, right? We'll conjecture that it is approaching 0. Right, so that's not so bad, hopefully. So again, here's another one. Very, very similar. It's, I think it's the same problem. Not really. The terms are a little different. But if you look at all these terms here, all these points down to the 10th term, now looks like, again, the terms are approaching a value of 0. So pretty quick one there as well. All right, so this time we're asked to determine the limit ourselves. Now, I could make a graph. All right, so watch this. All right, so I'm going to go to Desmos and enter this and plug in bigger and bigger values of n and see what happens to the terms of this sequence, right? So the sequence there, again, I'm going to call it f of n. Now you could do x instead of n. There's nothing wrong with that. And then I'm just going to plug in whole numbers, right? We're plugging in whole numbers for x. So instead of n, I'll put in x. You got negative, square root of x minus 7x over 8x, right? So negative, and then the numerator has square root of x minus 7x all over 8x, I believe. Yeah. And look at the graph of this thing. And you see as I move to the far right, 20, 30, 40, 50, 60, blah, 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 it looks like it's approaching some horizontal line, right? It's not going up forever or down forever. In fact, let's look at a table for this and see what happens when I plug in larger and larger values of, x, right? I know normally it would be n, but I'll do x. So 10, 0.835, 100, 0.8625, 1,000, 0.87. And you see the larger and larger I put in my input, the output's not getting the output's not getting huge positive or huge negative. It's approaching some finite value that's around 0.874, 0.8749. In fact, I'm going to guess that it's probably 0.875 because you see the 999 here. Now 0.875, that is 7/8. All right, so I'm going to conjecture that the limit is 7/8. Now if I graph the line y equals 7/8, look at this, right? Zoom in here. You see that green, again, you might not see green and red, but the bottom graph here was the graph of our sequence, and the red graph is 7/8, y equals 7/8. You see how it gets incredibly close. The further out I go, the graph is basically so close to y equals 7/8 that it's on top of it. It's as close to 7/8 as I want. So I'm going to say the limit is 7/8 for this sequence. All right. Now, that's not technically how we should be doing these. All right. You should be doing these the way you did limits in Calc 1. All right, so I'll write out how that would be done. So we're taking the limit as n approaches infinity of, negative, and then we have the square root of n minus 7n in the numerator divided by, and then 8n in the denominator. And you see there's a problem here where in the numerator, if I just leave things the way they are, square root of n would be going to infinity, minus 7n's infinity. You got infinity minus infinity up here. Remember, infinity minus infinity was one of those indeterminate forms. And then, it doesn't really matter what the denominator is. I've got something that I can't tell, right? Infinity minus infinity. Remember, there were others. There was infinity divided by infinity, or 0 divided by 0. Infinity minus infinity, 0 times infinity, 1 to the infinity, 0 to the 0. I think it was infinity to the 0. No, not infinity to 0. There was another indeterminate power. Yeah, there were lots of indeterminate forms here. Well, I believe the other one was yeah, it was infinity to the 0, right? Power. They were indeterminate powers, but yeah. So I got something indeterminate here. It's sort of refreshing your memory. One, two, three, four. Yeah, 7 of these. I remember them being 7. Anyway, so I got indeterminate. So I gotta manipulate this expression some way so I can find the limit. Now this might ring a bell. For something with square roots involved, I can multiply by the conjugate of that square root thing up top, multiply by the square root of n plus 7n, and then do the same thing down here, multiply by the square root of n plus 7n, and then we'll have, the limit as n approaches infinity, and then you got, I'll keep this minus sign out here. Now when you multiply two conjugates, right, you get a difference of squares, so that'd just be n minus 49n squared. And then down here, I'll just keep it as 8n times the square root of n plus 7n. That's actually silly. What am I doing? That's really pointless. Sorry, that was actually pointless. Because if I distribute the 8n here, right, we'd have negative 49n squared up top as the highest power divided by, and then down here you have 56n squared to be the highest power of n. And so, like, those dominate, and then you got, yeah, this is negative 7/8, and then we got the opposite of that, right? All right, so that was bad. I could have just left it initially, sorry. Or, so let me go back to the beginning. That was an unnecessary step. My apologies, right? Square root of n minus 7n, and then down here divided by 8n. Now remember, you factor out the highest power of n, right? When we're taking limits at infinity, factor out the highest power of your variable from the numerator and denominator. So like up top there, if I pulled n out, right, this is n to the first, this is n to the half. Then you'd have 1 over the square root of n, right, would be n to the negative half times n, that would be square root of n, and then minus 7. And then down here, you got the negative out front, and then 8n, and then the n's will cancel. And this term here, right, this 1 over square root of n, that goes to 0 as n goes to infinity, right, because we have 1 over some huge number. So the numerator is going to minus 7. The denominator is going to 8. This is going to 7/8, right? So yeah, so you can, sorry, that conjugate thing was unnecessary. I could have just done it straight up like this, factoring out the highest power of n. Yeah, so either way I look at it, if I look at a graph, if I look at it algebraically like I did in the paper there, the limit is 7/8. The terms of this sequence. And you could write out terms if you wanted, right? I showed you a bunch in the table, right? Like this would be the 100 billionth term, 0.87499 something, right? The terms of the sequence, if you wrote out a bunch of terms, are approaching 7/8 or 0.875. All right, so yeah. All right, so they're doing it again like calculus, replace n with x, and then they're just telling you it would be 7/8. Yeah, they don't really show you how they saw that. Hmm. Okay. Anyway, 7/8, great. So another one where we're determining the limit of the sequence. So again, I'll think of this as a function of x, and that way it'll be like calculus. You could also leave it with n's and just, again, treat it like you would in calculus. You know, take derivatives with respect to n when we're using L'Hopital's rule or whatever. So determine the limit of the sequence defined below. So I have the nth term is the natural log of 8n divided by n to the fifth. And if I look at that as a function, right, because these are functions, right? All these sequences are functions. I'll call nx. We got the natural log of 8x divided by x to the fifth. And you see as I go to the far right here, 5, 10, 15, 20, 35th term, 45th term. I mean, you can see that it's definitely approaching the x-axis, right? I mean, it's not going to be actually on it. I mean, I'm zooming in as far as I can there, but it's approaching 0. It looks like it's approaching 0. And if I go to a table, plug in, 10, what's the 10th term? Look at the 10th term is ridiculously small. Over times 10 to the negative fifth would mean move the decimal place to the left 5 places, so it'd be 0.00004. So even the 10th term is really small, and the 100th term is even smaller. The 1,000th term, even smaller. The 10,000th term, this is approaching 0. Right, so from a graph, I'm saying the limit of this sequence is 0. Now, again, if you were doing this by hand, going back to your Calc 1 limit laws and finding limits in Calc 1, I'd be taking the limit as n approaches infinity of, we have the natural log of 8n in the numerator divided by n to the fifth. And I'm just going to treat n as I would x, back in Calc 1. Well, the numerator would be approaching infinity, right? The denominator would be approaching infinity. So again, I have one of these indeterminate limits. And, infinity over infinity or 0 over 0. Remember, I could try L'Hopital's rule. So that's where I take the derivative. Now, again, I'm going to treat n like x. So this would be just differentiate with respect to n. So this would be 1 over 8n times 8 in the numerator, and then 5n to the fourth in the denominator. 8's cancel up here, and then this becomes just the limit as n approaches infinity of, 1 over 5n to the fifth, and that would definitely be 0, okay, because the denominator be getting gigantic and the numerator is always 1. So, yeah, so no matter how you look at it with a graph or with stuff, the way you found limits, L'Hopital's rule, all that junk from Calc 1, you can say it's 0. All right. Okay. So back to the graph thing. Now look at this, all these terms of the sequence, they're graphing out. Your fourth term's -8, fifth, look at that. All these terms eventually are just -8. So the limit of this sequence is -8. I mean, the terms of the sequence are definitely approaching the value of -8, and that's it. There's another one where -5 looks like the limit. All the terms of the sequence are approaching this horizontal line at -5. So the limit of the sequence is -5, easy enough. All right, so that graphing objective is pretty nice. Right here, determine the limit of the sequence below, if it exists, right? We haven't seen any that didn't exist yet. Now here, look at the sequence, the terms of the sequence. Now 13 over n plus 14. Again, I'll go graph this thing. Call it a function of x. Now we have f of x equals the cosine, and just make sure I'm in radian mode here. Yeah, we got radians, okay. It was the cosine of, 13 over n plus 4. Let's say 13 over, x plus 4. And again, what we're looking for is what happens at the far right. And it does look like it levels off, right? It's not going up forever or down forever, and it's not waving back and forth between two values, right? It's approaching a single value. And if I make a table, plug in, the 10th term would be 0.59, the 100th term is 0.992, the 1000th term 0.999916117, the 10,000th term is point. Look at all these now. After a while, it's basically so close to 1 that they say it's 1. This definitely has a limit of 1. Now think about that, right? 13 over n plus 14. If n got huge, right, you let n go to infinity, get bigger and bigger, this would be approaching 0. And then what's the cosine of 0? That was 1. Remember, so this will be approaching the value of 1. Great. So here, again, I can replace n with x and look at it on a graph if I want. So f of x equals, what was it? 5 times -½ to the nth. So 5 times, and then, -½ to the, I'll call nx. And now you see that because it's a negative number to a power, you get this like, because if x is some fraction, like a half, if you have a fraction with an even denominator, this will be imaginary. So that's why there's a lot of gaps in this. But look, all these terms, all these values here are approaching the horizontal axis. If I go to a table, plug in, what's the 10th term? 0.0048. What's the 100th term? Really, really small. What's the 1000th term? Even smaller. Right. This is definitely approaching 0. Right. And that's also something you should note. I'll state that on paper here. If you have a number that's between -1 and 1, space here. So if a number is between -1 and 1, then the limit as n approaches infinity of that number to the nth power will be 0. Yeah, so like in this example here, it was, -1/2 to the nth. That's going to approach 0 as n approaches infinity, right? Yeah. Numbers between -1 and 1, when you raise them to higher and higher powers, get smaller and smaller and smaller. Or if it's negative, get bigger and bigger until they approach, 0. They approach 0. So that's something good to know for future problems. Right. Yeah, so this limit is also 0. Right, cool. Next objective. Use properties of bounded and monotonic sequences to determine convergence. Right. A bounded sequence just means that it falls between two values all the time. It doesn't go up to infinity at any point. It doesn't eventually get down to negative infinity. It's always between some finite values. It's bounded by finite values. Monotonic just means it's always increasing or always decreasing. So if you were to graph, it's eventually always going up or eventually always going down, or you know, or it could be constant. It could be level the entire time. That would be considered monotonic as well. But yeah, so bounded means not going up to infinity or negative infinity ever. It's always between, finite values. Monotonic means it's, eventually going up forever. It's eventually increasing all the time or eventually decreasing all the time after some point. All right. So this here, 7 over, 2n plus 5. If I look at these all right, so determine if the sequence is, they say is sequenceable is bounded. So I'll write this out. A sub n is, 7 over 2n plus 5. Now I'll tell you this. This is important to know. If a sequence converges, if it has a limit, then it will be bounded. Then it is bounded. Right. Now be careful. The converse of this is not true. So like this converges, doesn't it, right? The limit as n approaches infinity of this sequence up here, this it would be 0, right? The denominator will get larger and larger and larger. So that means we have a convergent sequence, right? It has a finite limit, so it is bounded. It's always gonna fall between some finite values. Uh, and in fact, I could tell you what those are. Right? Say I started here with n equals, 1. Say that's where we're starting the sequence. So we'll have n be greater than or equal to 1 here. Now every single one of these values, 7 over 2n plus 5, every single one of these values is not negative, right? They're greater than or equal to 0. So we would say that the sequence is bounded below by 0, but it's bounded below, right? All the points, all the terms of this sequence are larger than negative numbers. And since n's greater than or equal to 1, 2 times n would be greater than or equal to 2, and 2n plus 5 would be greater than or equal to 7. And then, again, these are all going to be positive here. So when I flip them, that'll flip it over, right? 1 over 2n plus 5 will be less than or equal to 1/7. And then I multiply by 7, that 7 over 2n plus 5 will be less than or equal to 1. And this is for all n, in greater than or equal to 1. This is for all n in our sequence. So all the terms of this sequence are going to be greater than or equal to 0 and less than or equal to 1. Now this is bounded above by 1. So yeah, if you're both of these things, bounded below by some value or bounded above by some value, they call the sequence bounded. Right? And I can show you that in a graph too. If I were to graph this, now be careful, we're only plugging in whole numbers for n, n equals 1 onward. So when I look at, f of x equals 7 over, 2x plus 5, I'm not looking at the entire graph here. Right? We're only focused on when n is 1 or greater, and we're only supposed to focus on the ones with whole numbers. All right, so when I make a table, 1, just focus on the blue dots. All right, as I put in whole numbers, 4, 5, 6, right? You're only supposed to be focusing on the blue dots here where the input is a whole number. You see it starts off with an output of 1, and then it just keeps decreasing And since it's always decreasing, they would call this monotonic. Right? Again, monotonic or monotonic sequences are either eventually always decreasing or always increasing. This never rises after x equals 1 here or n equals 1. Right? You have 1, 1, you have 1, 1, 1, 1, and then after this point, it's falling, right? Never rising. That's monotonic. If a sequence at some point never falls and always rises, that's monotonic as well. That's what it means to be monotonic. But yeah, you see this here. I look at the terms of this sequence. Start throwing more points out here. 7, 8, 9, right? The terms of the sequence are definitely approaching 0, definitely a convergent sequence, and they fall between these two values, right? They're bounded. Y equals 1. I saw on my paper that the value of the sequence is always between 0 and 1, between these two bands here. It's bounded by these two horizontal lines. Every term of this sequence will fall between these two. All right, so that was a lot to say that the sequence is bounded, but the sequence is bounded. Now, be careful. All right, I said this, be careful. This statement I wrote goes this way. If a sequence is convergent, then it is bounded. The other way around is false. All right. So I just want to warn you here before I get to the next example. Be careful. If a sequence is bounded, it may not be convergent. It might not be convergent. It could be, but it might not be. For example, say a sub n here was, negative 1 to the n. If I were to graph terms like this, you'd have 1, negative 1, then negative 1 squared is positive 1, negative 1 cubed is negative 1, fourth is positive 1, fifth is negative 1, and so on. They would just keep alternating back and forth between negative 1 and positive 1. This is bounded, right? I can draw a horizontal line that's always above this. I can draw a horizontal line that's always below this, right? So the sequence is bounded, but it's not convergent, right? These points are not approaching some horizontal line, right? There's no finite limit. The limit, as n approaches infinity of this sequence, is just non-existent, right? It's not going to infinity or negative infinity, but it's not approaching a specific value. It keeps alternating back and forth, between negative 1 and positive 1. So just be aware that just because a sequence is bounded, it doesn't mean it's convergent. But the other way around is true. If a sequence is convergent, then it will be bounded. It will fall between two horizontal lines. Just please be aware of that. And they explain bounded and unbounded and stuff like that here. All right, so this is just determine the limit, what happens as n goes to infinity. So again, I can get a rough idea with a table. I'll show you how to do it with handwork too. There's something called the squeeze theorem for limits that will help out here. But so let me go back and enter this as a function. All right. So again, I'm replacing n with x. F of x equals 12 times the cosine of x over x. And let's see what happens as you go to the far right. Again, I don't care about all these points, just the ones where x is a whole number. All right. And it looks like it's approaching the horizontal axis here. It looks like it's approaching 0. All right. And if I were to make a table again, the 10th term of the sequence, -1, the 100th term, 0.1, the 1000th term, 0.006, the 10,000th term. And you see how it's getting very, very small, as I plug in larger and larger values of x, right? That's incredibly tiny. So it looks like from our table, from the graph, that the limit is 0. All right. Now let me do this on paper and talk about something called the squeeze theorem. Now you saw a squeeze theorem or a sandwich theorem. You might have heard this referred to as the sandwich theorem in Calc 1. Right? You probably saw something similar to this in Calc 1. So if I have these sequences, say A sub n, B sub n, and C sub n, and this inequality is holding true for all n greater than or equal to, some capital N. So eventually, right, what this is saying is, and these two outer ones, the an and cn, have limits that exist, and they're both the same. So, and the limit as n approaches infinity of a sub n is exactly the same as the limit as n approaches infinity of c sub n, these two outer ones. Let's say this is L, and so here's L on the horizontal axis, and then what happens is, after some capital N, right, after some value on the little n axis here, I'll do an in pink. So like say the terms of an are always lower than the terms of bn and always lower than the terms of cn. So say an's doing this, but it's approaching L. Right, so there's a sub n terms, and c sub n, is always higher, right? And approaching L again. If I've got these terms of a sequence called b sub n, and they're always in between. So like first, after this point, in between, they're always in between. Well, they got to approach the same limit then. They're kind of squeezed in to approaching the same limit. So if I have an inequality like this, if I have sequences that satisfy this triple inequality here, double inequality, and the limits of the two outer ones, the lower one and the higher one, are the same, they're approaching the same thing, then that middle one's got to approach the same thing as well. Then the limit as n approaches infinity of b sub n must also be L. Right? Must also be the same. So that's going to help us out here. All right. Because we're given this sequence 12 times the cosine of n, over n. And just remember that cosine of a value is always between, -1 and +1. And since we're talking about n, being some positive whole number here, I can multiply everything by 12 over n, and it won't change the symbols, right? It won't flip the inequality. So we'd have -12 over n on the left, then 12 cosine n over n in the middle, and 12 over n on the right. And this is going to be, the true for n greater than or equal to 1. All right, this will be true for n greater than or equal to 1. And I can show you in the graph here. Back to the graph, I'll zoom this back out. And let me put in this -12 over n, and I'll just use x though. Like say g of x equals, I'll just do y. Y equals 12 over x, and y equals -12 over x. And look it to the right of 1. Right? From 1 onward, the blue graph, which is our original graph, is between the green and the red, So it's always between them. And see how it's being squeezed. All right, the wavy graph is being squeezed into, approaching 0, approaching the horizontal axis. So I got this inequality holding, and these two outer expressions. Sorry, let me go back to the paper. So I got this inequality holding for n greater than or equal to 1, and these two outer expressions, -12 over n and +12 over n, had the same limit. Right, the limit as n approaches infinity of -12 over n is the same as the limit as n approaches infinity of 12 over n, and both of those would be 0. So, by the squeeze theorem, I'll just say by the squeeze, this middle expression, the terms of that sequence have to be approaching 0 as well. Of 12 cosine n, over n is also 0. And so back here, I'm just typing in, 0. Now I know you're at home doing this with, again, you can always use the calculator to help you out, make this a little quicker, but I just wanted to show you that the squeeze theorem would be nice to apply here. And they definitely do that down here. See the squeeze theorem being mentioned in the answer explanations. Great. Okay, this is just determine whether the sequence converges or diverges. We actually saw something like this earlier. I think it was the natural log of 8n over n to the 5th. I would do L'Hopital's rule, and this would approach 0. If you have n approach infinity, this would approach 0, so the sequence does converge, right? This is very similar to an example we saw earlier. And read through the answer explanations. You can look at a table, see that the values are approaching 0. Yeah. All right, here, determine if the sequence below converges, using the monotone convergence theorem. All right, so I'll write out what that says. All right, I'll write out what that says. So what is this monotone convergence theorem they speak of? So this is if the sequence, say a sub n, is bounded and monotone or monotonic, then the sequence must converge. It must have a finite limit. All right, so really what you're seeing here is, case one, so again, suppose it's bounded. All right, if it's bounded above, well, let's say bounded, so it's between two horizontal lines. And monotonic means it's eventually never falling or eventually never rising. So say these are the terms of the sequence at 1, at 2, at 3. But say it's always falling. Well, if it's always falling, it's got to approach some limit, right? It can't get below this horizontal line, so there's got to be another horizontal line that the graph will approach. So if it's bounded and always falling, it'll converge. It's got to approach some horizontal line. And the same thing if it's always rising, right? If you have so I'd say it's bounded by these two lines, and then say it's always rising, never falling. It's got to approach some horizontal line, right? It can't come back down at any point if it's monotonic. It's always falling, always rising, always decreasing, always increasing after some point, and bounded, the sequence has to converge. That's the monotonic convergence theorem. So the question is, are these things happening? Are these things happening? Is the sequence bounded and monotonic? Now the sequence we are given here is bounded, all right? But I don't think it's monotonic. So we have a sub n is 7 times the sine. Ooh, maybe it is. Never mind. 3 pi, we'll see. 3 pi n over 2 plus 1. The reason I say I don't think it's monotonic is because sine, remember sine and cosine, those are waves, so this is going to be something wavy. But again, it might not be because of this whole times 3 pi over 2 thing here. Now I know it's bounded though. Or I can tell you at least that much. Is it bounded? Question mark. Well, we know that the sine of anything, so the sine of this for sure is always between -1 and 1, no matter what you plug in for theta. So no matter what's in here, this is theta. You're going to be between -1 and 1. And if I multiply by 7 and add 1, we'd have -6 over here. 7 times the sine of blah plus 1 would be, so it's definitely bounded. All right, the terms of this sequence, and this is a sub n here, the terms of this sequence fall between these two lines, the horizontal line at -6 and the horizontal line at +8. Now, so yes, bounded, but is it also, monotonic? Now let's look at some terms of this sequence here. I'll just put, we'll start with n equals 1. Let's start with n equals 1. Now, every single thing here is going to have a multiple of 3 pi over 2. Now remember, sine of 3 pi over 2 is -1. So it starts off at -6. And then when I plug in 2, you have the sine of 3 pi. And remember, the sine of any multiple of pi is 0. So you're getting 1. 7 times 0 plus 1. And then when n equals 3, you got, 9 pi over 2. Remember, the sine of an odd multiple of pi over 2 is going to be 1 or -1. Now, 9 pi over 2 would be 1. That's going 8. And I think it's just going to keep bouncing back and forth between all these. Like, when I plug in, that's 1, 2, 3. When I plug in 4, again, I'm getting some multiple of pi in here. That'd be 0. So plus, just 1 again, then -6 again, and then 1, then 8. And this is going, up, then down, then up, then down, right? It's definitely not monotonic. There's never a point where this is always rising or always falling. It's rising, then falling, then rising, then falling, then rising, then falling, right? So again, I figured that would be the case when we had sine. If you have sine or cosine, probably a good chance that it's going to be rising, then falling, then rising, then falling, right? Because remember, sine and cosine are waves. Now let's take a look at this in a graph as well. So once again, don't focus on the entire graph, right? I just want to put in points that have a whole number inputs, right? 1, 2, 3, 4, 5, and so on. So our sequence here was, 7 times the sine of 3 pi x over 2. See the rising and falling there, all right? And then we have plus 1. Again, I don't want to focus on all these points, just on the ones where x is a whole number. So 1, and then 2. Look at this. Look at the blue dots here. Then 3, then 4, then 5, then 6. And you see it's -6, 1, 8. 1, -6, 1, 8. -6, 1, 8, 1, -6, 1, 8, 1, -6, 1, 8, 1. It's just going to keep doing that. So see look at the graph here. It's, sorry, get off this. So you see, follow the blue dots. You have 6, 1, 8. 1, -6, 1, 8, right? Those are the terms of my sequence. And it's never always rising or always falling. It's not monotonic ever. It never eventually is always rising or always falling. So because of that, we can't say anything, right? Because again, the theorem says, all right, here's the theorem. Again, this is if it's bounded and monotonic, then it must be convergent. Not the other way around. Now, we saw in the graph that it's not convergent, or sorry, the inverse is not true. Sorry, the inverse is not true. So if one of these is failing, then it must be not convergent. You can't say that. Because I could have a thing that waves up and down, but gets smaller and smaller. I could have a sequence like this where things are waving up and down, but then they're approaching some horizontal line. This is not monotonic, but still convergent, right? So you can have something that's not monotonic, but still converge. So just because one of these fails doesn't mean you can say it converges or not. So yeah, so you have to have both of these to say something converges, but if one of them fails, it could still converge. Well, actually, it's got to be bounded, right? Because I said earlier, if it's convergent, then it's bounded. So if it's not bounded, then it's not convergent. But this one, if monotonicity fails, it could still converge, and we have that here. Monotonicity fails, right? This sequence is not monotonic, but so it could still converge. I know it doesn't. Right? You can clearly see that from the graph. But if I didn't have a graph, I couldn't use this theorem to say it converges or not. So it can't be determined. It can't be determined. So read through this. They talk about the theorem. So determine if the sequence below converges, and if so, find its limit. If the sequence diverges, enter this. Look at this. You got -4 over n plus 2 in the power here. If n got huge, that would be approaching 0. So this would be approaching 5 times e to the 0. E to the 0 is 1. This is approaching 5. Right? You could make a table or look at a graph, right? But you're going to see that as you go to the far right, as inputs get larger and larger, this will approach the value of 5. Right here, so look at this. 4 to the nth. That's going to get gigantic. So we have -1 minus and then infinity. This is going to minus infinity. This is going to get huge negative. All right, you can see that in the graph again. I'll just do the graph once more here. We have, again, I'll call n x. We have a -1 and then minus and then 4 to the n, 4 to the x, divided by 3. And look at this. See how it's going down. Now, once again, you only care about when it's whole numbers input, but when I plug in whole numbers here, the 10th term is negative 349,000 something. The 100th term is huge negative. 1,000th term is, the 1,000th term is so big, it just says it's undefined. So it's going to negative infinity. This is not convergent. This is what they call divergent. Right? The sequence would diverge for sure. Now, determine if the sequence below is monotonic. All right. So again, monotonic means always rising or always falling at some point. Now, I believe they want it to be from the beginning. I forgot to read their definition of monotonic in the answer explanations from earlier problem. But I just know that when I was taught, a sequence is monotonic if it is eventually always rising or always falling, right? It is eventually non-increasing or non-decreasing. Now look at this sequence here. We have a sub n is, n plus 2 over 4n. Now this would be 1/4 plus, 1 over 2n, right? So like you could start off if you want when n equals 1, a sub 1 would be, 3/4, right? That's a1, sorry. 3/4, and then a sub 2 would be 4 over 8 would be a half. So this is 0.75, here's 0.5, and then a sub 3 would be 5/12, which is even smaller, right? I guess I should put these as this is 9/12, here's 6/12, 6/12, right? This is 5/12, a sub 4, yeah, 6/16, right? 3/8, which is if I make this 24ths, 10/24ths, and this is 9/24ths. I don't know. It just looks like it's decreasing the whole time. All right, now a way to really double check that, decreasing, that means that, the n plus first term is less than or equal to the nth term, right? Every term is smaller than the term previous to it. So let me take a look at a sub n plus 1. What would this look like when n is replaced by n plus 1? Now, if n is replaced by n plus 1, that would be 1/4 plus 1 over, 2n plus 2, right? Because it'd be 2, I'm replacing n with n plus 1, right? So it'd be 2n plus 2 in the denominator there. And let's see what happens if I say that it's less than a sub n right now. See if this leads us to a bad statement. We can get rid of the 1/4, and we have 1 over 2n plus 2 would have to be less than or equal to 1 over 2n if it's decreasing. And these are, of course, positive if n is greater than or equal to 1 here. These are positive values. So then flipping these over gives me 2n plus 2 would have to be greater than or equal to 2n. And subtracting 2n gives me 2 greater than or equal to 0. This is a true statement. So if I went backwards, if I started with this statement here, say we know that 2 is greater than or equal to 0, and then I add 2n to both sides, which wouldn't change the inequality. Then I flip things, and then I add 1/4. We can see that a sub n plus 1 must be less than or equal to a sub n. So this is a decreasing sequence. This is monotonic then, right? It is monotonic. It's always falling, all right? And if you wanted to, again, you can make a little graph here and see, we got f of n, f of x equals, x plus 2 in the numerator divided by 4x in the denominator. Now this graph should be approaching a quarter, right? The limit should be a quarter. But you see here, starting at 1, right? You see it's falling. It is falling, as I stated, right? So it is monotonic, right? Monotonic is always rising or always falling, or never rising, never falling after some point. Now let's see. So they do. So their definition is at some point. So you can have a sequence that's rising, then falling, then rising, then falling. But if it eventually starts to always rise, or eventually starts to always fall, then you have a monotonic sequence, right? Because they see here it's always for all n greater than or equal to some n sub 0. Right? And so they showed, you know, like I said, that a sub n plus 1 is less than or equal to a sub n, for n greater than or equal to 1. So it's, decreasing monotonic. Right, so this one's very similar. We saw one earlier with a sine. Remember cosine here, that this is not going to be monotonic. It's going to be rising and falling, rising and falling, rising and falling. And remember, if a sequence is bounded and monotonic, it will converge. But if it's not monotonic, still bounded, this would still be bounded. This would still be between 4 and 12. You can see that in the graph, or remember, because cosine is always between -1 and 1. And then multiply by 4, add 8. So this is bounded, sure. But if a sequence isn't monotonic, this is not always rising or always falling eventually. This will be rising and falling, rising and falling, rising and falling all the time. So remember, if it's not monotonic, you can't say anything with this theorem. Right? This theorem, you need both this boundedness and monotonicity to be considered convergent. If you don't have one of those, you can't say anything. So convergence, once again, cannot be determined by this theorem. This is very similar to an earlier example with sine involved instead of cosine. All right. All right. So now, does this converge or diverge? I'm just going to tell you right now. Remember from Calc 1, right? This is limits, just like limits in Calc 1. As n approaches infinity, you can look at a graph, look at a table, look at a chart, right? But remember, exponentials grow much faster than polynomials. So like my numerator is an exponential function, e to the 8n. The denominator is a polynomial function, 7n to the 8th. The numerator is going to grow much, much faster than the denominator. So this is going to infinity. Then you could apply L'Hopital's rule a bunch and see that, the numerator will never go away. It'll be there will always be an e to the 8x or e to the 8nth in the numerator. The denominator will eventually get down to some constant. It's a polynomial. When you keep taking derivatives, you'll eventually get down to some constant. So this is going to infinity. This is blowing up. This is not going to some finite value. So the sequence diverges. All right, so I'm just going to say that. Again, they show you, they make a little table here, but again, you should have recognized hopefully that, hey, the numerator's got an exponential, the denominator's got a polynomial. This is going to blow up. This is the same problem pretty much. You have an exponential in the numerator, a polynomial in the denominator. As n goes to infinity, the numerator is going to get much, much larger than the denominator will ever be. So this is going to infinity. This is diverging again. This is very similar to the previous example. All right, very nice. All right, and last objective, determine whether a function converges or diverges. All right, so now we're back to treating this like you would in calc. So remember there was a problem earlier with, it was like the negative square root of n minus 7n all divided by 8n. And what happens as n approaches infinity? Again, you might remember from calculus, calc 1. This is a polynomial over a polynomial. I remember highest powered terms dominate. So this would be like having, if n goes to infinity, negative 7n squared will dominate the numerator, 3n to the fourth will dominate the denominator, and that reduces to negative 7 over 3n squared. And negative 7 over 3n squared would approach 0. So this will approach 0 as n goes to infinity. This does have a limit. And again, you can go to a table, go to a graph, see that the output, as n gets larger, or x gets larger and larger, this will get smaller and smaller, and we'll be approaching 0. All right, so again, I'm just kind of speeding things up here. This should all be pretty much like a Calc 1 review. I'm not going to go through all the Calc 1 stuff again. Now they do apply L'Hopital's rule, they're saying here a few times, but a couple times, just once really. This is pretty much the same thing. You got a degree 2 divided by a degree 4 polynomial here. Look at the lead terms, or you could do L'Hopital's rule. This would be infinity, negative infinity over negative infinity, right? You could apply L'Hopital's rule. But as n goes to infinity, this would be like having negative 9n squared over negative 5n to the fourth, right? The dominant terms, which would reduce to positive 9 over 5n squared, and that would approach 0, right? The denominator would be getting huger, faster than the numerator, which would always be, 9. So this is also approaching 0, right? Remember, for your rational functions, if the polynomial in the denominator has a higher power than the numerator, it's going to go to 0 as the input gets larger and larger and larger. And once again, you can make a table, make a graph, see that this thing will be approaching 0. Great, and that looks like it. All right, so not a lot of tough problems here at the end. All right. Great. So that's it for the assignment, this preview of the assignment, right? Remember what I said in the beginning. The problems you see at home may not be the same problems I saw here, but the objectives are the same. The way I did them would be similar. Talked about them. So hopefully watching me do these here help you out when you're working on them on your own. I'd say the most important things to take from this would be the definitions and the theorems, So what does it mean for a sequence to be bounded? If you a visual way to think about that is if you're looking at the graph of the sequence, it's always falling between two horizontal lines. Right? It never gets higher than some value, never gets lower than some value. What does it mean for a sequence to be monotonic? Right? That means eventually the sequence terms are always rising or never falling, or they're always falling or never rising. Right? Eventually increasing, eventually decreasing sequences are called monotonic. Then you put those two things together. If you have a sequence that's bounded and monotonic at the same time, that will have to converge. It's going to be convergent. Um, Now, again, if something's bounded but not monotonic, you can't say anything with that monotone convergence theorem. You can't tell if it's convergent or not. Then there was another statement I had where if a sequence is convergent, then it will be bounded, but not the other way around, right? If a sequence is bounded, it might not be convergent. You don't know. And then you have the squeeze theorem, right? If one sequence is always between two other convergent sequences and those converge to the same thing, the sequence in the middle will converge to the same thing as well. Lots of stuff here. So hopefully you're reading the text, reading the extra instruction, not just watching these videos, right? And because I didn't cover every possible little example, right? I'm sure there's examples where things were always increasing or limits, didn't exist and things were divergent and stuff like that. Right. So be aware, hopefully you're reading the text. And the textbook stuff is coming from is mostly the openstacks.org calculus volume 2 text. So if you go to there, should uh, should also help. This is in their section 5.1 on sequences. All right. Sorry for the long outro here, but thank you very much for watching.